guys. Welcome, stats students, to Section 4.5, Probability and Counting Rules. Section 4.5 really wraps up this whole chapter. This is a compilation of everything we've done. So now that we've learned the fundamental counting rule, right, that's when we do the number of possible outcomes, multiply them together. We're going to use that. And the permutation rule, remember, permutation rule, order matters. And that's when we do the permutations, obviously, on the calculator. And the combination rule. So combination rule is when order does not matter. Just a little helpful hint. Most of our problems, I'd say maybe 99.7% of our problems in Section 4.5 are going to be combinations, not permutations. So we can use those three things to compute the probability of outcomes of many, they call them experiments, but many situations. So all of this comes down to the probability of any event E. I don't know why the book switched to probability of an event E when back in the beginning we talked about the probability of event A. But probability of any event is always favorable over possible. So every single one of these problems, there's no new material. It's using everything that we've done in Chapter 4 and putting it all together. So there's no other words to write except for doing some practice. Be patient with me. I got calculators everywhere and papers and everything else. So let's start off with scheduling workers. I think if we do a solid job at this, we probably don't need to talk about a ton of other examples. Maybe we'll talk about 27. So scheduling workers. Suppose a manager supervises 16 women and 12 men, and each shift needs 8 people. Part A says, find the probability that exactly 3 women are selected to work the shift. All right, for some reason we need to know that. So if we're going back to our formula, our crucial formula, favorable over possible, I always start with possible because possible is going to be the same for every one of these A through D. Because possible is we've got 16 women and 12 men, and each shift needs 8 people. Does it matter in which order those 8 people are scheduled to work a shift? It really doesn't, right? They're just going to show up and work. So this is going to be a combination. So our possible is going to be a combination. How many people do I have to choose from? I have 28 people, right? Don't forget, we have to put those together. So I have 28 people to choose from, and I'm choosing 8 to work that shift. So my possible for every denominator is going to be the answer to 28 combination 8. I don't know if you've got a calculator out, but check me later. I've got that as 3,108,105. Please, please, please check my math. I will redo the whole recording if it's bad math. So every denominator for A through D is going to be 3,108,105. So now each question is its own favorable. That's going to be our numerator. So find the probability that exactly 3 women are chosen to work the shift. All right, so that means think about the probability, what you have to find. We're going to find the probability of 3 women, right? But how many people are working? 8. So that means if there's exactly 3 women, there have to be 5 men working that shift. Does that make sense? It still has to add up to 8 people working. We can't forget about the other one. We can't just say 3 women and that's it, because it says 8 people. So it's an and in the middle. Hopefully you remember, what does and mean? And always means multiply, right? So I'm going to have 2 parts for my favorable. The probability of the 3 women and then the probability of the 5 men. So my favorable is going to be the probability of 3 women. Do we care in which order those 3 women are chosen? We don't, right? As long as they show up to work. So it's a combination. I have how many women to choose from? 16, and I'm wondering about the probability of 3 of them. The probability of 5 men, So still a combination because we don't care what order they show up or what order they're scheduled. So how many men do I have to choose from? 12 men, and I'm choosing 5 because that's the rest of the shift of 8. The and tells us to multiply those guys, and my denominator is going to be that 3, 108, 105, because that is going to be the denominator, my possible for every single one of these problems. So when you do your calculator, hopefully you've got the TI-84 or app figured out. You can do those. I usually do 16 combination 3. I hit an equals, and then I multiply it by 12 combination 5, or do the 2 of them, whatever works best for you. When I did that numerator, I ended up with a, oh gosh, what did I end up with? I can't see my little tiny writing. 443,520. It would not hurt right now, especially for that first problem, to actually try it and make sure you get that answer, because sometimes you know what you're doing, but it's the actual calculator work that gets messed up. And that's still going to be over 3, 108, 105. You know the story. We have to simplify our fractions. And these problems come out to really crazy numbers. So if you turn that into a decimal, I believe it's like 0.143 or something like that. My calculator simplified it down to 128. Where do I write this? I'll write this over here. 128 over 897, or approximately 0.143 for part A. Sorry for it crammed in. I probably should have just put fewer problems and given you a lot more space to work with. Put a sticky note or something if you need more space. Please remember to either simplify or turn into decimal form. When we get into scientific notation, I'm going to tell you just leave it in fraction form. The graphing calculator turns decimals into fractions. If you use the math button, the first choice is a little arrow to a fraction, so if you've got a decimal. I think we should talk about B, because the probability that no women are selected to work. So that means we're looking for the probability of 0 women, which means we still have a full shift, right? So that means I've got to have 8 men then. So that's going to be my favorable over my 3 million for my possible. So we've already decided, I hope that you're with me, that this is a combination. The order does not matter in which order they show up to work as long as they're there. So my probability of 0 women, so I've got 16 women to choose from, and I'm choosing 0. For the 8 men, I've got 12 men to choose from, and I'm choosing 8 of them. And tells me to multiply, and that's all over 3, 108, 105. You might be shocked to learn that 16 combination 0 is 1. There is one way to choose 0 people. And 12 combination 8 ends up being, I believe that's a 495. Over 3, 108, 105. When I simplified that down, I got a 1 over 6279. Or if you go to a decimal, that's going to be one of those scientific notation. I believe it's a 1.59 times 10 to the negative 4th or something like that. Remember that negative 4 tells you to move the decimal 4 places to the left. So it's going to be approximately 0.00016. That's such a tiny decimal, highly unlikely, by the way, because it's so close to 0. But I think 1 over 6279 just looks better. It's a little bit easier to see, to understand. Not a very good chance that no women are selected, especially since there's more of them, right? Find the probability that all of the people selected will work the shift, or to work the shift are women. So the last one was 0 women. This one is all of them. So the probability, and how many are all of them? It's got to be 8, right? Not 16, because a shift has 8 people. So we've got 8 women working. Don't forget the other part. That means we've got 0 men working. So typically you are going to have 2 parts. So 8 women working. That means I'm going to have 16 combination 8 times a 12 combination 0. The and tells me to multiply. The 12 men, I'm picking 0 of them. 16 women, I'm picking 8 of them. That's all going to be over my 3,108,105. So check my math on that. I believe when I did that, I think that's a 12,870. 12,870 over my 3,108,105. When I simplified that guy down, I got 2 over 483, which is approximately 0.0041 maybe, something like that. All right. So it's using all of this probability stuff and combining it all at once. I do want to talk about D. I know you're probably tired of this scheduling situation. However, the probability that at least one woman is selected. Here's that at least one situation. So that means it could be 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8. That seems like a lot, right? If you want to visualize it, we have 0 women, 1, 2, 3, 4, 5, 6, 7, 8. So here's all the possible amounts of women that could be working a shift. At least one means 1 or more. So basically what it's telling me is that I have to find the probability of all of this. And since it's 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8, I'd have to add all those separate probabilities together. I don't know about you, but that feels incredibly exhausting. Think about it, probability always adds up to 1, right? If I could find the probability of this side, I could subtract that from 1, and it would give me the whole highlighted part. So this is where that at least 1, if you can picture it, does help out. So at least 1, we could just find out 1 minus the probability of 0 women. I keep spelling it wrong. And then I would have myself an answer. Don't forget, we also in every single one of these problems had to say, well, if there's 1 woman, there's 7 men. So I have to multiply that part of the probability problem. And then if there's 2 women, there's 6 men. Multiply those guys. In the end, I got all these things to add together. So this seems like a lot less work to me, and I should probably add then, if it's 0 women, it's got to be 8 men. I hope that you're looking up at problem B, because we already found the probability that 0 women and 8 men would be working, right? We found that that was 1 over 6,279. So if I'm going to treat this and make life easier, because at least 1 is supposed to make life easier, I could instead do 1 minus that probability answer from letter B, 1 over 6,279, and I'd have myself an answer of 6,278 over 6,279. Or if you prefer, 1 minus the 0.00016, which whatever that comes out to, 0.99984. So pretty high probability that you'll have at least 1 woman, because it was pretty low probability that you'd have no women. So part D is actually a lot easier than it looks, and it's a great example for how that at least 1 works. All right, let's talk really quickly about some house colors. There's 5 houses on a cul-de-sac. It's in a restricted neighborhood. You have to ask permission for everything. And you are only allowed to choose 3 colors of paint to paint your house. You can pick beige, blue, or yellow. So those are exciting paint choices. How many different color sequences are there? Now, first of all, are there repeats allowed? Are you allowed to have more than 1 house be beige, more than 1 house be blue, right? So possible, because you can, because remember how I said favorable over possible, I'm always going to find possible first. The A and B are the favorable part of the question. So possible, I've got 5 houses, 2, 3, 4, 5, and all of them are going to be able to choose what color paint. Well, how many paint colors do they have to use or to choose from? 3 different paint colors, right? And the second house has 3 different paint colors. The third house, the fourth house, and the fifth house. Fundamental counting principle says that I need to multiply. If there are repeats allowed like this, typically the line method is the easiest way to figure out your possible. So repeats allowed, I use the line method. It makes the most sense to me as opposed to a permutation or a combination. So if I do that, 3 to the 5th power, what is my possible going to be equal to? Like 243, I believe that is. So all of my denominators will be 243. So letter A actually is asking possible. How many different color sequences? So that's really asking possible outcomes. Well, we already did the math for that. That's 3 to the 5th power, or 243. Letter B is an interesting question because it's bigger than it looks. What's the probability that all 5 houses would randomly select the same color? So we can't just say the probability of the same. That's not going to work, right? Because it could be the probability that all 5 are beige, or all 5 are blue, or all 5 are yellow. So we've got ourselves a multifaceted problem here. So let's just focus on one thing at a time. What's the probability that all of them are beige? Interesting question, right? Well, it's a combination because it doesn't matter who gets painted what. How many houses do we have to choose from? And how many are getting painted? 5 houses to choose from, and all 5 are getting painted. Beige. Well, here's the thing. All blue, we've got ourselves a combination. Doesn't matter who paints first. 5 houses are getting chosen, and 5 are painting blue. And yellow, whoa, don't want to do that. Yellow, we've got the same situation going on. We've got 5 houses to choose from, and all 5 are being painted yellow. What does the OR tell us we're going to do with these? Add, right? So we can do this. I'm going to just do this part first, and then we'll put the use that as our favorable. So this is our favorable. So 5 combination 5, pull out your calculator. I don't know if you remember this from earlier, but 5 combination 5, any combination when you're choosing everything is always a 1. So 3 different outcomes if we're choosing all the same. Well, that's our favorable over our possible. So you have 3 chances out of 243 that they're all going to be the same color. 3 out of 243, I believe, is a 1 over 81. I think if you're going to a decimal, that's going to be something like 0.123. So you get about a 12% probability of all 5 houses becoming the same or being painted the same color. So this is really about practicing everything in the chapter, putting together permutations and combinations, putting together ands and ors, putting together the line method if you're using, if you've got repeats and everything's being used. So a lots of amalgamation of everything in the chapter. Favorable over possible is our most basic. That's what we started in 4.1. So hang in there, lots of practice. We'll spend some time on this and make sure that you are getting the hang of things, watch for ands and ors. I know there's more practice. We can do some more practice as we go along. And thanks for sticking in there for section 4-5.